Welcome again. Today we are going to talk about the input impedance of a difference amplifier. Input impedance of a difference amplifier. Let me quickly copy the circuit of the difference amplifier. Now, what is input impedance? What is input impedance in general? Okay. If I have a complicated circuit, very complicated circuit, in this box, inside this box, and it has many passive elements, resistance, no active source at okay, for say for example, then and say one of the nodes in this circuit is taken as the reference or grounded 0 volt. It has a input terminal, it may have some outputs. Now, what we can do, say we can connect a voltage source between this input terminal and the ground, call it V plus minus, this side plus, this side minus, and if we do so, it may draw some current I. Okay. Then we will call the input impedance of this terminal is this input voltage divided by this input current. Okay. So, input impedance this is equal to input current, sorry, input voltage divided by input current, input voltage divided by input current. Okay. So, this is the input side. This is the complicated network in a box or a circuit. And it is passive, means it has only resistances, for example, no active source, no voltage source, no current source. Okay. This is equal to V by I. This is in general the input impedance. Now, if a circuit, in general, if a circuit or a network has multiple inputs, so this is a network okay, and it has multiple inputs, say call it input 1, another is input 2. This is the reference terminal or ground terminal of this network. Now, we can connect multiple sources, maybe one source like this, call it V2 plus minus, you can connect it like this, or if you like you can also connect it like this. Then when you apply this voltage, it will draw some current, call it I2. Then you can also then you can define the input impedance of this terminal, input impedance of this terminal 2 This is V2 by I2. Okay. Similarly, if you connect, instead of connecting this voltage source here, if you connect another voltage here, plus minus, if this is V1, and if then it draws a current I1 here, then input impedance of terminal 1, here also input impedance of terminal 2. This will be V1 by I1. Okay. So, okay, do not apply this voltage sources one at a time. When we apply this V1, do not apply V2. When you apply V2, do not apply V1. Okay. Apply V1 and V2 separately. Okay. That in general, I mean, if you are finding this input impedances in an experiment in the lab by applying some voltage and measuring this current with an ammeter, then apply this one at a time. Okay, because it's possible that when you if you apply V1 and if you also have V2 connected to simultaneously, then V2 may affect this current I1, V1 may affect this current I2. So, in general, we should apply one voltage source at a time. So, this is the note: apply one source at a time, or make the other source equal to 0 when you apply the other one. So, this is one way of defining input impedance. Now if we have many terminals, we will have many input impedance for each of the individual terminals. Okay. Another way we can define input impedance, say if we have a network with two input terminals. This is a circuit with two input terminals. We can apply a differential voltage like this, Vd plus minus, connected like this without any common ground. Okay. So, then a current will flow I. If this current is I, this current must also be I. Why? Because of conservation of charge. Okay. You just think of this part of the world. So, from this part of the world, only one wire goes out and one wire comes in. So, if I want to conserve the charge inside this, then whatever current goes out, same current must come in. So, both these currents are same, they have to be same, I and I. Okay. So, now I can define the input impedance in this way. For this type of connection, input impedance, this will be equal to this voltage Vd divided by this current I. We have no confusion about which current to take, this current or this current, because both of them are going to be same, they have to be same. Okay. But if we had a common ground, then let me draw it and then I will erase it. If I have a common ground, then it is not necessary that these two currents are same, because there is another path through which current can go in or out. So, then there is a question, which, so if then I call this as I1, then as this as I2, should I put I1 here or should I put I2 here? I do not know. But when I do not have this ground, then I know I1 is equal to I2 definitely, and then there is no confusion. You can put either I1 or I2, or you just call them as I, just put this. Okay, so this is another way of defining input impedance for some circuit where you have two terminals and you can give a differential input. Okay, so this is what is input impedance in general. Now let us come to the difference amplifier. Okay, which is here. Okay. So it was not necessary here. Let me cut, paste. So now we come to the specific case of our difference amplifier. So coming to our difference amplifier, diff amp. Okay, so now we, as we have said, we can connect this in two different ways, one with a common ground, another without a common ground. So first let's take without common ground. Without common ground. So how we will connect the input? So let me connect the input this way. A voltage source which I will connect between these two terminals V1 and V2. Let me call this side as plus, this side as minus. Let me zoom in. Plus and minus. So this is the input, okay, and this is the output, and the circuit I will seal it in a box. Okay, so it has two input terminals, one output, and I connect a differential input without any common ground like this. Then of course you can immediately recognize that these two currents here and here must be same. If this is I, same current must come back, right, because of the conservation of charge. And now if I call this voltage as V, what you can call it, VD or VI, I for input, or D for difference between these two, whatever. Okay, so then the input impedance is how much? Then the input impedance I will define it as this voltage VD divided by this current I. Input voltage by input current. In this case, the voltage is a differential voltage applied. Okay, so let's now find out this is equal to how much. Okay, now you observe that we have proved previously that Vn will be equal to Vp if we do a detailed analysis of this circuit, because in this circuit virtual sorting is going to work. Okay, so these two will be at the same potential. Now let us apply KVL, Kirchhoff's voltage rule, in this path, in this along this purple circle. So in this loop let's apply KVL. KVL in this this purple or violet loop. So what can we say? Let's start from this point. So Vp, and then here, starting from here, I have a potential drop IR1. I is flowing in this direction, so it's a drop. So minus IR1, then another drop, because plus side is here, minus side is here, so this is another drop whose magnitude is Vd. So minus Vd. Then here another drop IR1 minus IR1. So this will be the potential Vn. Okay. So this will be equal to Vn. Vp minus this drop minus this drop minus this drop is Vn, right? So from this we can write that Vp, let me bring Vn to the left side, minus Vn minus IR1, IR1, there are two IR1, so let me write 2 IR1 minus Vd, this is going to be equal to 0, right? Now we know Vp is equal to Vn, so this part is 0. So from this we can write that minus 2 IR1 is equal to Vd. Okay, and then from this we can write that Vd by I, this is equal to minus 2 R1, right? This minus sign is coming because I have chosen I in this direction. Okay, I should have actually chosen I in the opposite direction, because if I am applying this voltage with plus here, then I am interested in how much current is drawn out from this plus side, because this voltage is trying to drive the current in this direction, right? So this voltage source is trying to drive the current in this direction, so I should better write I in this direction. Okay, so let me take also this I in the opposite direction, this is also I. So everywhere in this equation, wherever I have I will just put minus I. Okay, so this will become plus, this will become plus, this will become plus, this will become plus. So therefore this will become plus. Okay, I did a small mistake, that's why I got this quantity negative. So now this is what? This is nothing but the input impedance. This is the input impedance. Input voltage by input current, input impedance. This is equal to 2R1. Okay, so I should take the current in the proper direction. This voltage source is trying to drive the current in this direction, so I should take it in this direction. Otherwise, I will run into this trouble of plus minus symbol. So this is the answer. So let me write input impedance of this difference amplifier is this times R1, where R1 is this resistance. Okay, and this is for this type of connection. I repeat, for this differential connection without common ground. Okay, great. Now let's come to the situation where we have inputs connected in a different way. How? Like this. Instead of connecting the input like this, I can connect, say, one voltage source plus minus like this, between this and the common ground here, or I can also draw it like this. This means this terminal is connected to here, okay, right? So then I have only one source, okay. So now let us find the input impedance for one terminal at a time, individual terminals. Okay, so this voltage is applied, which is V1. So this is applied, and this, so I have to take the current, this current I, this is the input current, this is the input voltage, this is the input current. So now the input impedance will be equal to V1 by I1, input voltage by input current, right? What should I do to this terminal V2? I should apply no voltage to it, or I should apply 0 voltage to it. Okay, so that's the rule. So this is also connected to ground. Okay, so I told you in general, when talking about a network, we should have, which has multiple inputs, and we want to find the input impedance of each terminal, we should apply input voltages one at a time. So I connect the other input to 0, so no voltage is applied there. So now let us find, you can find this current, and then you can find the input impedance. So how much will be this current? Okay, so now you see, observe, with this terminal grounded, that means this terminal is actually grounded. This part acts like a inverting amplifier. Observe that with V2 equal to 0, this is V2, the amplifier acts as an inverting amplifier. Okay, so therefore we can use the derivation that we did for inverting amplifier, and we can directly write that VO is going to be equal to V1 multiplied by minus R2 by R1. Okay, so this we can write directly, or you can do a thorough analysis. Once again, no problem, you will get the same result. So this, if this is VO and this is V1, okay, and therefore you can find this current. How much will be the current? The current I will be equal to V1, this is V1 minus VO divided by R1 plus R2. This will be equal to V1 minus, in place of this I write plus V1 R2 by R1 whole divided by R1 plus R2. This will become V1 multiplied by R1 plus R2 divided by R1 multiplied by R1 plus R2. So, this will be equal to V1 by R1. Okay, you can actually do it quickly. You can also do it quickly. Another alternatively, so you just observe that this point is at 0 potential. This is 0, this is 0, so this is also 0. So alternatively, so you can do this in many different ways. Okay. So this is 0, this is 0. That means Vp is equal to 0, since V2 equal to 0 and this is also equal to 0. So that means Vn will also be equal to 0, because we know for this circuit virtual sorting works. We have seen that. Okay. We know that this happens. Virtual sorting is true for this circuit. In general not, but for this circuit yes. If so, so then this is at 0. Now this is at V1. So how much will be this current? I. We can directly write this current I is V1 minus 0 by R1. So this directly gives I is equal to V1 minus 0 by R1. Same as this V1 by R1. Okay. So this is simpler. So therefore, input impedance is equal to how much? V1 by R1 is same as V1 by I. This is same as R1. This is for terminal or port 1, okay, for terminal 1 with the other terminal grounded or 0 voltage applied. Okay. So this is the input impedance for this terminal. Similarly, you can find the input impedance for the other terminal here. Okay. So similarly, we can calculate input impedance of terminal 2. How? So this is the circuit where instead of applying this voltage source to terminal 1, I will apply it here. So I erase it and I apply this voltage source to this terminal. Let me call it V2, and this terminal should be grounded. Okay. Otherwise, if there is a voltage here, that may also affect this current. Okay. So now I have to measure this current I2. Okay. And then the input impedance will be V2 by I2. So I have to find the value of this current I2. Okay. So you just observe that the current will flow like this. Okay, current will flow like this. No current can flow here. Therefore, what can we say about this current? So this is at 0 potential, this is at 0 potential. So and the current only flows like this. So how much will be? So okay, you can also connect this. 2, right? And no current flows here. These two are at same potential, you can connect it. So you see how much is I2? I2 is nothing but this voltage divided by this total resistance, right? So that's it. Now from this you can write that R1 plus R2 is equal to V2 by I2, right? And this is what? This is the input impedance. Input impedance of terminal, this is 2. That's simple. So therefore you can either calculate the input impedance of the two terminals individually, or like this. So this is for terminal 2 and previously we did for terminal 1. Or you can also define an input impedance in this way: when a differential voltage is connected like this between the two terminals without any common ground between this source and this part of the circuit, then you know these two currents are same. So you can define the input impedance as this voltage divided by this current, and we also have found the expression for that. So in this case the input impedance was here 2R1, sum of these two resistances. And if you define input impedance for individual terminals, then for terminal 1 this is equal to R1, and for terminal 2 this is equal to R1 plus R2. Okay, thank you.